The reality is glial cells get no love, despite the fact that they do all types of insulation and structure and transportation for and did you want to be in the video? Jonah?
Okay.
Okay. You sure? Sure you don't want to be in the video? He brought me a cat who he said was going to throw up, and then you really did want to be in the video? I'm teaching about glial cells today. You know, Schwann cells, oligodendrocytes, astrocytes, ependymal cells, satellite cells, microglial cells. You know about those?
No.
Okay. Well, what things do you think your mom does for you? What things that you don't do for yourself that your mom does? What are they?
Make food.
Makes food. You gotta come be in the picture.
Does my laundry.
So cleans up after you?
Yes.
That's what glial cells do for neurons in the brain.
Okay.
Yeah. And sometimes doesn't she pick you up?
Yes.
And support you?
Yes.
Basically, glial cells are like parents.
Where's Dogger? Right. Thank you.
I want to talk to you about a real problem. Glial cells get no love. So, your brain consists of neurons that communicate with each other, and they get all the fanfare, they get all the accolades. They're the star point guard of the basketball team that's shooting all the threes. But you know, without his friends on the basketball team, that star point guard is nothing. Without all of his political advisors, that particular candidate is nothing. Without all of her friends who help her make the star of the show, she is really just one person. Glial cells are the glue of the nervous system. Literally, that's what the word glial means, is glue. But they don't actually stick the neurons together. They do more of what could be considered a support. My cat's gonna throw up. I gotta go. Back to glial cells. So our glial cells, again, are the support systems for the neurons, and they are far outnumbering the neurons, so that you have far more glial cells than you have neurons, despite the fact that neurons get all the accolades. So unfair. Anyhow, let's talk about your central nervous system. Your central nervous system is divided into two halves. One being your brain, which is up here in your skull, and the other part being your spinal cord, which runs down, starting at the base of your skull, all the way down to your tailbone, or your sacrum, and coccyx. It doesn't quite go into your coccyx, but that's for a different anatomical discussion. So that's your central nervous system. The goal of the central nervous system is to provide input to the body, and to move the body around, and then to seek out information from the world based on the body's sensory neurons. Those are specialized cells that we'll talk about in the next chapter. And so your brain is a processing center for all of that. It is also the seat of consciousness, which we'll talk about after we do sensations. The peripheral nervous system is every neuron, or nerve, in your body outside of the brain and spinal cord. You might be asking yourself, well, what kind of nerves do I have outside the central nervous system? And you have lots of them. In fact, running down your neck, out your arm, out to your fingers, you have motor neurons that go out to the muscles in your finger, starting in your spinal cord, going all the way out there to your arm. You have neurons that are signaling those muscles to move. Similarly, if you touch a hot substance, you have neurons that are in your fingertip that are detecting temperature change, heat, and something called vibration or displacement. All those neurons are specialized, and we'll talk about them when we do sensation and perception. But the idea is that they are neurons that send signals back up that cord into your spinal cord, and then the spinal cord puts it up to your brain, where you generate, or somehow, some way, a sensory experience is given or experienced by you. We don't know. We have some limitations on our understanding of consciousness, and again, that's for a future chapter. But what you should know is that your body is full of neurons, and they're supported by glial cells. You got two distinctions of your nervous system: the central nervous system, the brain and the spinal cord, and the peripheral nervous system, all those nerves that are outside in your body that run down your legs and out your arms to your internal organs. Also, let's talk about another distinction of your peripheral nervous system. You have, sorry, I'm distracted by this bird who's feeding its babies. You can probably hear that right now. Babies are quite loud. I was going to talk to you about your sympathetic and your parasympathetic nervous system. So the sympathetic nervous system is the nervous system that's engaged when you're stressed, when you're aroused, when you are ready for action. And the parasympathetic nervous system is that's engaged when you're tired, when you're going to sleep, when you're waking up, when you've slowed down your metabolic processes. Netflix and chill, rather than going out and playing pickup basketball. That would be a fight or flight, or a sympathetic nervous system. If you were in your parasympathetic nervous system, you'd just be standing in a corner in the game and wouldn't be helping your team. If you were really amped up during Netflix and chill, you wouldn't be that chill. What's going on inside of a cell? Something called the resting potential is that your neurons have a steady state. Homeostasis is the idea that they stay at the same level. I am not at my steady state quite yet. I've got to fill up my tank with some drugs here. So inside the neuron, there are a bunch of ions, and if you remember your chemistry class in high school, ions have an electrical charge to them. Ions like sodium, potassium, chloride, those are all positively or negatively charged. If you have a ton of positively charged sodium ions inside the cell, you'll have a positive electrical charge. If you have a ton of chlorine in there, you'll have a negative electrical charge. And the resting state inside of a cell is negative 70 millivolts. It just stays there until something happens. We discussed this before, that as a neuron gets information from other cells, it might get two types of information. One, it could get an information that says, hey, get more excited. Get information saying, hey, get less excited. So how does it do it? The cell has a semi-permeable membrane. What that means is that the surface of the cell, so if you imagine a long tube, like say, the surface of it has areas where you could get into it. These channels, and the channels can open and they can shut. It also has pumping stations where it's pumping in and out of the cell from the extracellular space. It's pumping in some ions and pumping out other ions from the inside. And what that does is it shifts the balance of positive to negatively charged ions in the cell. I'm taking a very long time to explain this, but this is happening in microseconds. It's happening extremely quickly, and as it happens so quickly, the system goes like this. It's negative 70 millivolts, but then as it floods filled with sodium ions, that potential, right, that positive electrical potential continues to rise rapidly, and we call that an action potential. As it goes up, it hits the peak amount of positive ions that could fit in there, and then all those sodium ion channels openings close down and don't let any more sodium in, and the pumps keep pumping out positively charged ions so that it'll go back down. It'll stop being so electrically charged, and that happens as a wave chemically across the cellular membrane of the neuron. That wave is the action potential that we see, and it's going down the cell to the terminal ends where something else is going to happen, and we'll get to in a bit. But that's the idea, is it changes the cellular composition inside the cell to represent a positive electrical charge, and that there are mechanisms by which that happens. Pumps and channels. I would say any questions at this point, but I know there are too many to answer. Recognize that you don't need to necessarily understand exactly how this happens right now, but this is the beginning of you understanding, and if you proceed into the neurosciences, you're going to get more and more of this, and it will become a model for understanding nerve impulses that is helpful. I'm here to talk to you about a major problem in America right now. Roving bands of marauding peoples traveling to large fields for battle. Who I'm talking about? Club soccer players. Why I'm talking about club soccer players, maybe you played club soccer, your kids played club soccer, is that amateur athletics has come under great scrutiny recently. And for good reason. Science is telling us some stuff about the benefits of athletic involvement for children, but also some of the detriments. Recently, if you read in the Scientific American journal, you'll see in 2018 a report on amateur women and men's soccer players. And what they found was an astounding sex difference in brain injuries that they really don't have an answer for. But what they found is that women deteriorated much larger areas of brain tissue, and these are women without a history of head injury. It's not like these are women who have mild traumatic brain injuries. And men had far less, on average, brain damage, and in far less regions. So you had these two giant discrepancies between the types of brain injury that men and women were experiencing, both playing soccer against their own sex. And what you find is a giant difference like that, and people tend to shirk away from it. People tend to get nervous about that. We live in a world where we are focused on equality, and this is an important focus. But we can't lose sight that we are biologically different creatures from male and female. And this is clear evidence that we are not the same physically, that we have different outcomes for a similar type of activity. It's really important to understand that we don't know why there's brain damage more so for female amateur soccer athletes than for male amateur athletes. We're not sure about that. So don't go around claiming you know why, that it's because women head the ball more or they have less musculature in their neck. You don't know. No one's done the science. So don't go spouting something like it's truth. A really great way to do it is to say, I wonder if. Okay, so we have this evidence. Men and women are different in the amount of brain injury they get from playing amateur soccer. We know that. But don't go around saying women shouldn't play soccer, or only men should play soccer. That's a stupid idea. Don't say stupid things. Say, I wonder if the risks for female brain damage in playing soccer makes it less worthwhile for them than for males. That's a good way of saying something that people could then take in and understand, rather than be put off by your statement that sounds to them sexist, mostly because of the time we're in, or because they don't know you. Maybe that's not your meaning, but try to state things like a scientist would. I wonder if, or hypothesize that, rather than big conclusatory statements that are just going to be off-putting to everybody else. I look forward to hearing your questions about this research that was done at Albert Einstein College of Medicine by Dr. Lipton, neuroscientist, excuse me. Look it up. It's pretty awesome. They used MRI. The next subject is neurotransmitters. We already discussed that Santiago Ramon y Cajal found that the neurons in the central nervous system didn't touch one another, that they had a gap between them called the synapse. And that synapse is something that allows for the chemical communication between neurons, but how it happens is that at the end of each of those neurons, I told you I'd tell you about this later, so here's where, they have a tiny sacs in the terminal ends called vesicles. And vesicles are filled up with these proteins that are stringed together, these amino acids that are stringed together into proteins called neurotransmitters. You got all sorts of them. You got acetylcholine, it's abbreviated ACH, or if you like to say acetylcholine, if you want to be French about it. Dopamine, you've got glutamate, you've got serotonin. These are sort of the workhorses of the nervous system and communicating between neurons, or interneuron rather than intraneuron communication. And they also, those are generally speaking excitatory neurotransmitters. So they're sending those EPSPs, or the excitatory postsynaptic potentials, the signals to say to the next neuron, get more excited. There is also, serotonin can be inhibitory. GABA is the main or the primary inhibitory neurotransmitter. So your brain uses GABA. GABA is gamma aminobutyric acid. So we just say GABA for short because it's a lot easier than saying gamma aminobutyric acid. So GABA is used to inhibit neurons. So if you wanted to tell that next cell, hey, you got to calm down, GABAergic neurons would be used to decrease the cellular signaling of that particular neuron. So those are neurotransmitters. The basics is they are stored in vesicles at the terminal ends of their particular neuron. When the action potential comes down that axon and then hits that terminal button, it releases, those vesicles kind of explode open. And they release their contents. So the contents of the vesicles is released into the cellular space between. The space between being the synapse. And for lack of a better thing to do, they float across. Actually, I have no idea what the mechanism is to get them across. I think it's just a really short space until, like, happen circumstance, they just go to the other side. I don't know. I should better myself by figuring out what the mechanism for the transportation of neurotransmitters is. Nonetheless, they float from the vesicles to the postsynaptic neuron, right? So there's two neurons here. One's got the terminal end with the vesicles. It releases those neurotransmitters. The other one is a different neuron, and there's a gap between the two, and that's synapse. On the other side, or on that other neuron, there are things called receptor sites. So receptor sites are another protein structure. Again, the nucleus that has that little DNA structure, and it has in there the instructions for how to make all these different types of receptors. You got all assortment of different receptors. But let's say serotonin looks like a triangle, and this receptor is GABA, and it looks like a square. So if that triangular neurotransmitter tried to get into the receptor site that didn't have its shape, this neuron is not going to get any GABA signaling. It's also not going to get any excitatory signaling. So until that triangular serotonin reaches the triangular serotonergic receptor site, that communication between the cells isn't going to happen. Some people call it a lock and key analogy. Okay, I never really got that. I understand why they would use it. I didn't like that analogy. I always thought shapes was a little better. If you have a round neurotransmitter, let's say this is acetylcholine, and you have a round receptor, acetylcholine fits in there, and then that postsynaptic neuron that has the receptor site now gets a positive or excitatory postsynaptic, see, post after the synapse, synaptic transmission. So the EPSPs, or the potential. So that's the idea of how neurotransmitters work. And the way we could change neuron functioning is by messing with those particular things that I just told you about. You could mess with the neurotransmitter side, or you could mess with the receptor sites. These are called antagonist and agonist actions. The antagonist actions are those that reduce the effects of a neurotransmitter. So basically, if you send in a little glue that like hits up those acetylcholine sites, and it sits in that site, and it doesn't allow for that rounded ACH neurotransmitter to come in there because this is a blocked receptor, you've acted in an antagonistic way. If you want to act as an agonist, you might say increase the level of signaling. So you might make that cell produce more of a particular type of neurotransmitter. Some antagonists you might be familiar with are things like Botox. So if you want to get rid of all these wrinkles up in your head, you can inject an antagonist, and what it does is it goes in and does that same thing that I talked about. It gets into the acetylcholine receptor site, and it sits there. And so the acetylcholine is the major one that makes all these muscles tense, makes you have all the wrinkles. And what it does is it blocks the cellular signaling for those muscle fibers so they all relax. And you get these people that look like they have faces that don't have any life in them. They're so beautiful with all their Botox.